Hello, thank you for joining me to talk about thinking in the elementary math classroom and how our different learners think and share their thinking in our math classroom. During our time today, we are going to be talking about how our students can use tools to support their thinking as well as externalize their thinking. And also be talking about the understanding of the number line progression in our elementary classrooms. So before we begin to really use some of these tools and talk about thinking, let's talk about our math classrooms and ways that we're using tools and manipulatives in our math classroom. Dr. Peter Liljedahl, in his Green Elementary Mathematics book and Green K-5 task book, he gives us some ways that we can use manipulatives in our math classroom. So one way that we can use manipulatives is to think about the manipulatives. We would not be able to think if we did not have that number line in front of us. The number line gives us something to think about. So an example of that might be this question here: what's the difference between the jumps and the tick marks on the number line? You might call them tick marks, you might call them hash marks, just the lines and the points on the number line. So take a minute and think about what a learner in the elementary classroom might say about this. All right. We may also use the manipulatives or the tools. Here's an example of a tool because the kids aren't concretely manipulating it, to think with them. To where if I told a student what is 9 plus 7, they might say, okay, 9 plus 7, if I add one more, then I get a 10. So 9 plus 1 is 10, and then I need to add 6 more to be able to add my full 7. So 9 plus 1 plus 6 is 16. That's where using that number line is really showing how they decompose that 7 in order to find the sum. As a math learner who learned math a long time ago, this part is where, when I'm decomposing numbers and using those mental strategies, I usually myself need to support my thinking with a tool because there's so much flexibility. I need to visualize it to keep track of my thinking. Then we also use manipulatives and tools to represent our thinking. We have a lot of students who come into our classrooms and they are great with that mental math. They can say, okay, I know what 235 minus 161 is. I know that, hold on, let me think, 74. So that student knows 235 minus 161 is 74, but then we really need them to say how they know that. What would they do? So if they subtracted the hundreds and then they decomposed their tens into 30 and 30, so that way they got to that 105 and then subtracted 30 more, they see that this student didn't need to get to 100 to be able to subtract further. They have no problem counting back from 105 to 75. And that is what a lot of our naturally math-minded students can do. They just don't realize how they do what they do. That's where those students are using the manipulatives and the tools to be able to externalize what they're doing in their head. So, another mathematics model that we talk about within using manipulatives is the Lesch model. And we hear this a lot in math with our concrete representational abstract progression. Within that progression, there's lots of connections that our students need to be making and between the various representations. Starting with that concrete, where we have the student that has represented 3 times 4 with the color tiles, whereas this student represented 3 times 4 with the color tiles, but they drew this in their journal to kind of record their thinking there. So that's a semi-concrete representation, but it's still a visual that they're using to show that 3 times 4 is 12. So then when we get to something like 3 groups of 4 is 12, we see that 3 groups of 4 is 12. How do we know that 3 groups of 4 is 12? We know we have our students that are like, it's 12, let's move on with life. But then we need those students to see that it's 12 because 4 and 4 is 8, and that's a double. And then 8 plus 4 is 12. And so we need our students who understand math at that symbolic level to still be able to understand it when it's concrete or visual, verbal, and contextual, not just that symbolic level. And that is a challenge with some of our thinkers. So that's a lot of the math we're going to be digging into. Then when we think about the types of thinking that our students are doing, in our classrooms, we have divergent thinkers. We have students who see the connection between all of the different representations. Oh, I can use it to represent it with the 4 of the one color going across, but I can also make 3 of one color of my columns. So seeing all of the different ways and making connections between all of those different modes, that is where our divergent thinkers really thrive, making those connections. And I have become one of those divergent thinkers, seeing those connections and, oh, I can see it like this. And this is how I can understand that symbolic level of that. So our divergent thinkers have multiple possibilities and see all math in all of those different ways and see the beauty between it. We think of, Good Will Hunting, where we can see math all over the board. That is so much thinking, divergent thinking, maybe even, I wonder if it would even be convergent thinking. Speaking of convergent thinking, our convergent thinkers are focused on finding that most efficient path. We all have had that learner in our classroom that's like, yep, 3 times 4 is 12, right? I don't need to elaborate on that. I don't need to tell you why I got there. Stop asking me. Stop wasting my time. I just know 3 times 4 is 12. And so with our convergent thinkers, a lot of times we need to help them see other representations, because that's how they're going to develop that grit and that perseverance for when they don't always just see math at that symbolic level. Once they get to statistics or pre-cal, it's going to be a lot harder for them to understand that symbolic level. That symbolic might not come as naturally to them. So by having an understanding of the various representations, they can understand that symbolic level. And so then another type of thinking is that metacognitive thinking. We're not going to be addressing metacognitive thinking as in depth today, because in our math classroom, our convergent and divergent thinkers have to be metacognitive thinkers. they have to think about what they're doing and why they're doing it and making connections. So, as we're talking about all of our convergent and divergent thinkers in our math classroom, we're going to see that theme of metacognitive thinking. So the tools we're going to be digging into today are the number path and that number line. So that number path might be a little new for you, and you might look at that and what in the world is that, and why do we need, when and where do we use a number path? So take a minute and pause, look at the number path. What do you notice about this number path? We might even already see some difference in our thinkers here. We might have some that are like, it represents 20. I see that. And then our divergent thinkers might say, oh, I see it's got 5, anchored in 5. It's all the different things. So we will have all of those students in our classrooms. So we're going to take a minute and look at Christina Tondevald explain a little bit about the number paths.
How do we actually use a number path? Well, one of my favorite ways is to help our kiddos build number sense. For a lot of our students, when they think of 6, the only thing they think of is the digit 6. We want them to picture 6 things, okay? So let's say I give the number path to a student and I say circle 7. Most often, the number one way that we see kids circle 7 is they just circle where the 7 is. And so there are definitely ways I could rephrase that to make it more obvious, but I just want to put it out there to see what they do, what they think of when they think of 7. So oftentimes we get it where they just circle the digit where the digit 7 is. But in reality, that's not what 7 is. 7 is 7 things. So I want students to understand that when they're showing 7, it's not just the digit. It's 7 things. And so on a number path, we encourage kids to circle 7 things when they're showing 7. This also leads into, you can do comparison type problems where kids will show an amount and then show the other amount and talk about which one is more, which one is less, and then that can lead into questions like, how much more, how much less, which is the precursor to building in this idea of adding and subtracting. So when kids are adding and subtracting using a number path, the one thing I want you to know, you don't need to teach them how to show it on the number path. It's up to them. The number path is a model, it's a tool for them to use. There is no specific way a child needs to show their thinking on a number path. The one thing I do want them to do is to show their thinking. And I should be able to look at the number path and tell what they did. So if we were solving a problem.
All right. So we learned a little bit about the number path, and let's look at how that number path might be used differently with our learners in our classroom. So thinking about our divergent and convergent thinkers, how might our students approach this number path? So with our divergent thinkers, we've got lots of different possibilities, and our convergent thinkers, they see that most efficient path, right? And we know 11 is more than 6. 6 is less than 11. both of them need to have that metacognitive thinking on how they know that. So we have one student here who says, oh, well, I can see that 6 is less than 11, but 11 is 5 more than 6 because I see I've got 4 white and 1 gray here. And then 11 is the same as this 6 and this 5 more. And then that 6 is 1 more than 5. So I can see 5 and then 6 here. Like all the different ways and those relationships that we can have. Our divergent thinkers see the beauty in all of the ways that our numbers are related. 6 and 11 are related. But then we have that student who says 11 is greater than 6. And okay, well, how do you know that? Well, 11 is more than 6. Or 6 is less, I know 6 is less than 11. So see how they're using their answer to justify their thinking. So a lot of the times our convergent thinkers need support in that metacognitive process. So with our convergent thinkers here, how can we help this student understand at a deep level that 11 is greater than 6? So if our students are engaging with math in these different ways all of the time, I'm hoping that a student could easily say, or I might ask a student, okay, well, can you give me an example of when 11 might be more than 6? And if that student says, oh, well, if I have 11 Easter eggs and my sister has 6 Easter eggs, I know that I have more than her because when I put the piles next to each other, my pile was way bigger than her pile. So see how that contextual situation drives that? And we can also tell that that student has an understanding of the difference in magnitude, right? That they can see that their pile is going to be not just a little more than their sister's, but a lot more. And then that verbalizing of how they know that. And so with our convergent thinkers, they know 11 is greater than 6. But they need to be pushed out beyond further into why do they know that? How does that work? And remember, our convergent thinkers, they're the efficient thinkers. So when we're thinking in other contexts, they're thinking, why am I wasting my time in this? Because I know 11 is greater than 6. But will that always work? So with our divergent thinkers, they're using that number path to represent it. They're using the visual of, oh, look, the gray and the white with their justification. All of the different ways. And then that symbolic of, I know that 11 is more than 6. So our divergent thinkers really thinking of all of the different ways. But what our divergent thinkers also, what we need to be sure of is that they can hone in like our convergent thinkers. It is so great to see the beauty in all of the different ways that this is addressed. Now, how can we determine what the most efficient way is? And that's going to be different for our divergent thinkers. One might show the most efficient way using that contextual situation, where that other one might be more of the visual or the verbal. And so our divergent thinkers can sometimes be their own worst enemy by seeing all of the beautiful ways that numbers and math is connected, but we do need to be sure we support them in honing in to find those efficient ways as well. Because, like Christina Tondevald said, there's no specific way students would show their thinking on a number path. The same with all of the different representations. There's not one specific representation that students should use to be able to show their understanding of math. So let's look at another example of thinking in our math classroom. This one is hit the target. I love playing darts. My daughter loves playing darts. We can play darts all day long. So we have this dartboard that we used in our garage, and to win, you had to have 15 points. And I asked my daughter, I'm like, what do you want to do to win? And so my daughter, also a student in my class, might say, oh, I'm going to get a 10 and a 5 to win because I know that's the fastest way to win. And student B says, okay, I mean, I can get a 10 and a 5, but I might not get a 10 every time. I could get a 5, 5, and a 5 because that bullseye might be really hard for me to get. So student B is thinking beyond just the efficient way, right? They're like, oh, well, it's not realistic that I'm going to get exactly what I want in the order that I want it. I can get it all of these different ways. So by thinking about that, we can see the student A is thinking mathematically and they understand that's the most efficient way to get there. But are they thinking in a deeper sense about it? Well, is it possible to get to that 10 and that 5? Because it's within the contextual situation of playing darts, student A would be more likely to come up with a variety of different ways to get to 15 because they know it's not realistic to get there. And even student B's 10 and then 5 different ones. That's not realistic either, right? We might start with a 1 and get another 1, but then get a 10. So the context drives the flexibility here for student A to push them beyond the most efficient way to do that. Then that was at our house. I had a friend that taught 4th grade, and in her fourth, she was like, I love this. I want to do this in my 4th grade classroom. So, but my dartboard doesn't need to be that simple. These are 4th graders. We're stepping it up a bit. So in her 4th grade classroom, her dartboard had these different possibilities. We're in the middle of a game, and me and my partner, we have 25 points, and we need to get to 115 points to win the game. So we're asking the students in the class, like, what do I need to do to win? Student 5 or student A says, okay, well, I have 25. So if I get a 25, then I get 50. Another 25, 75. Another 25, 100. And then 10 for 110, and then a 5 for 115. So see how student A is like, let me give you the quickest way to get from A to B. And student B says, oh, well, like I can get a 5, so now I have 30. And then I'm going 40, 50, 60, 70, 80, 90, 100, 110, and then 15. But student B might even say after that, like, oh, but that's not very realistic either. I might do a 5, and then I get a 10, a 10, a 10, and then a 25, and then a 10. And so student B, that divergent thinker, might see all of those different possibilities. Does that mean that student A does not see those possibilities? So, right, our student A totally sees those possibilities. They just don't see the need for those possibilities. Again, that's where the context can drive the flexibility and that need for that metacognition there. So think about some students that you've had and how they might engage with math differently based off of the type of thinkers they are. We might have these students, they both understand math, but they might not engage in mathematics the same way. When I think of the way students engage with mathematics, I think of my Hadley. And Hadley did not care about efficiency. She loved being flexible within her mathematics and making connections. Oh, look, Miss Veazey, I don't need to do a 10 every time. I can do a 5 and a 5 and a 5. And while it was not efficient, she was so in awe of all of the different ways she could engage with the math. So with Hadley, she would come up with all of those different ways. And I would ask, okay, well, what is the most efficient way? If I said, hey, we have to do this really quickly, how can you do this? I needed to be sure that she also knew the most efficient way to do that, because she saw that beauty. She also needed to see the most efficient way. Whereas my convergent thinker, my Isaiah, he would just say, like, look, Ms. Veazey, decompose it by place value and then multiply, and like there I can find my product. And Isaiah did not really want to tell me any different ways or how he could multiply, because he knew that most efficient way. And he learned that standard algorithm for multiplication, and that's what he wanted to do. So with Isaiah, I really had to give him a reason to engage with the math at a deeper level. So he was there with that symbolic understanding of, like, I get the standard algorithm, I multiply my ones and my tens, and then my ones and my ones, and then my ones and my tens. So then thinking about, okay, well, how can we put that in a contextual situation? How can we use a visual to help us with that? Because those symbolic understanding, we need to have be sure that our convergent thinkers understand it in multiple different ways. So when it's no longer, when their thinking has capped, their understanding has capped, they have the metacognitive thinking to be able to make meaning of that. That's where a lot of our gifted learners can cap out when we get into later math. They don't need a number path to show me that 11 is greater than 6. But when they get to absolute numbers, get to statistics or pre-cal, they're going to need to have that flexible understanding to be able to get into math that's above their understanding. And that's where that learning happens for them. So we have to prepare them in elementary school to be able to be successful in any type of mathematics situation. And one of the things I think of when I think of our convergent thinkers in our elementary classrooms is when that computer coding, thinking of our STEM fields. If we only cared about the outcome in a computer, if we only cared that we could open Microsoft Word on our computer and didn't care about how we got to open Microsoft Word on our computer, we'd be in a very different place. We might not even be able to open Microsoft Word. Like, I only know to go to start my Windows and then click on Microsoft Word and it opens. Like, that's the only way I'm doing it. If that's not a possibility, I'm just not using Microsoft Word. But our students have to have those different ways, because we know computers don't always work the way that we need them to work. So while there is an efficient way to do it, we still need to be comfortable in different thinking. Whereas our divergent thinkers, they're seeing those connections and the beauty. Like, this is where I see our divergent thinkers. They're blowing with the wind, like, oh, I can see that when you say this, I've got there. And all of the different ways there. But do they ever stand strong in one way? Not unless we get them to. So we can do such a great job of getting our student divergent thinkers to see the beauty in math. But then what do we do to focus them in to be sure they also see the efficiency in math? Like our maze here, there's lots of different ways to get to the middle of the maze, or to get out of the maze. Look, there's my divergent thinking. We could go in, we can come out, however we want to engage with the maze. So our divergent thinkers see all of the different ways that we could do that. But then do they see that, oh, if I go this path, it is an efficient way? So we have a big task with our divergent and convergent thinkers in our classroom. How do we get all of them to be able to use manipulatives and use tools to share and understand their own thinking? So let's dig into our thinking through estimation. And we're going to dig into estimation with some, again, using number lines. So take a minute and read Van de Waal's definition of estimation. So, like he says, in everyday life, estimation skills are valuable. This estimation is one of the skills we utilize the most as adults. And so we want to be sure that our students are developing that at a young level, at a young age as well. So with some estimation, let's make an open number line and choose your endpoints. Where would you place 619 on your open number line? So pause the video, make an open number line, and put those endpoints on there and place 619 on there. Take a minute and pause. All right. You made your number line, so my number line, my endpoints that I chose are 600 and 625. And so I can tell that 619 is around 625. It's much closer to 625 than it is to 600. How do my endpoints compare to your endpoints? So we can see how different endpoints can be used to estimate the value of numbers. I use 625 because I love that compatible number of 25. Counting by 25s, quarters, all of the things. If I can use a 25, I'm going for it. And so then my transitions aren't here. Make a number line and you choose your endpoints for 326. You already see mine. Try to make your number line different than my number line. Go ahead and pause. Because I chose my 25 on my last number line, and I'm like, oh, 326, that is way close to 325. I didn't want to do 325 to 350. I could have done that, but it might bother a lot of people that my 326 is not inside my endpoints. I had my endpoint of 325, and then I just put my 326 next to it. So here it looks like 326 is my endpoint, but when I was actually in the process of making it, I did that 300, I made the 325 first. Using those number lines when we're showing what we're doing, externalizing our thinking, it doesn't always follow the process of what it looks like. And that's where we have to, that verbalizing going with that also helps with that process. All right, so were your endpoints the same as mine? You probably did 325 and 350, huh? I did not think about that until I actually looked at this here. And that's the point with our divergent thinkers. We see something new every time. So since we just estimated 619 and 326, think about how can we have different estimates of the same number? You said 619 was about 620. I said it was about 625. You said 326 was about 330. I said it was about 325. How can we have the same number but have different estimates for it? We know that estimation is in the eye of the beholder, right? Whatever numbers you're comfortable with, whatever numbers I'm comfortable with, that's going to impact how I engage with the math and how you engage with the math. And that's what we want our students to see. So let's estimate. What is 619 plus 326? Don't find the actual sum, but think about your estimates and what would the sum be. Pause and use your number lines. All right, so my estimate was 950 because I had 625 and 325. So there's my 900, and then my 25 and 25 is 50. So my estimate would be 950 because 600, I used those 25s both on both of them to do that. What would your estimate be the same as mine, or would it be different? So even with our divergent and convergent thinkers, we might approach this differently. Our convergent thinkers are going to like, oh, nope, the nearest 10, that's going to be like, I can do that for both of them. because that 25 might not have worked well for both of my numbers. It did here, and that worked out beautifully, but it might not all the time. So you might have a convergent thinker that just sticks with, like, I'm always going to find the nearest 10 because that's the most efficient way to do that. But we know that's not always going to be the most efficient way. So we need our convergent thinkers to think about, here is how I estimate it. Is this efficient? Is it always going to be efficient? And so we have to take their thinking and continue to expand it by using other examples and kind of showing, does this work every time? Whereas our divergent thinkers might say, oh, it could be 620, it could be 625, I could round to the nearest 100, and it could be 600. So our divergent thinkers see all of those different combinations, but then what is the most efficient combination for this problem here is what we really need our divergent thinkers to be able to hone in on. It's a challenge to balance between our divergent thinkers and our convergent thinkers in our math classrooms. Getting them all to see the need and have that metacognition around what are they doing as they're engaging in the math. Because a lot of time our convergent thinkers, they just see it and they don't want to continue digging into it because they know, especially in our kindergarten world, when they say, like, I don't need to move those to count those, I just know that's 23 because I can look at it and count it. Well, is that going to work when I no longer just have 23 objects, but now I have a pile or a big bowl of M&Ms in front of me? Do I need to move them and count them and organize them then? That's what we're getting our convergent thinkers to do. We need them to understand what they're doing now so that they will forever be able to understand what's happening and make sense of the mathematics. Develop that grit now so that they can always have that grit when they need it. There are some students like Einstein that math just always he probably never really struggled in math, or he lived in that struggle in math. But when we see our students, a lot of our students that understand math, especially at the elementary level, when they get to that secondary level, that math is no longer simple enough for them to engage with it at that symbolic level. They have to have multiple tools to be able to engage with the math at all levels. So I've got a couple more resources here that you can use to continue your learning. Take some time and choose one of those resources and dig into other ways that you can support your gifted learners, your different thinkers in your elementary math classroom. You can pause here and engage with that. And then once we end, take a minute and just kind of think about all the ways that we engage with the math. We use tools, we use number lines. So what's still circling in your mind? It can be about the number paths, the number lines, or it can be about convergent and divergent thinkers. So what's still circling after you have looked at those resources and listened, engaged with our math today? And also think about what is something that squares with your thinking, that you're like, I totally see this, I understand this, I can make connections to that. What squares with your thinking? And when you do that, hopefully in our time today, that we have talked about how we can use those tools and those manipulatives to not only support our thinking, but also externalize our thinking. We have so many of our learners that, or a third of our learners come in and they just get those number relationships and that. But we need them to be able to externalize what's happening in their mind. What do they get? How do they see that so naturally? And that's where our tools and our manipulatives and all of our different representations really support those students. Using manipulatives and using tools is not something that only our struggling learners use. All of our learners are using them because we all need engage with the math in a different way. And then hopefully you got some enjoyment out of using those number lines, the number paths, and the number for composing and decomposing, as well as some estimation. So many different ways that our students can engage in that number line, especially for our students who understand math. That number line is the easiest tool for them to use to externalize their thinking because it is so open. It can be used in however they engaged with the math because they can do the math. They just need to know what they do when they do the math. All right, thank you guys for your time today. If you have any other thoughts or research, please share them with me. I'd love to continue this journey on how our learners engage with math and thinking in our classrooms.